Okay, hi everyone. I think we can get started. So let me introduce our speaker today. Uh, so, okay, so we're very glad to have Dr. Nicholas Golledge with us. He's a professor of glaciology in the Antarctic Research Center at the Victoria University of Wellington. And his interest is primarily in understanding how Earth processes work, particularly in the context of climatic changes spanning centuries to millions of years. And he typically uses geological and paleo-environmental evidence to guide numerical model simulations uh, of the past or contemporary field glaciology to better understand and model modern ice sheet behavior with a focus on the Antarctic ice sheet and the connected Earth system elements. Dr. Golledge was lead author on the Ocean, Cryosphere, and Sea Level Change chapter of the IPCC Sixth Assessment Report. And prior to his current position, Dr. Golledge was Associate Professor, Senior Research Fellow, and Research Fellow at the Victoria University of Wellington. And he earned his PhD from the University of Edinburgh and bachelor's from the University of Aberdeen in the UK. And today, Dr. Golledge will be speaking on the topic Antarctica and the global climate system, observations, models, and chaos. And he's joining us very early from where he is now. So thanks for that. So welcome, Nick.
Great. Good morning, good afternoon. Sorry. Thanks for the introduction, Patrick. Yeah, so your afternoon, I appreciate you shifting the time for this a little bit. It makes it a little bit easier. It's 7 a.m. for me, so yeah, not too bad really. Hopefully you can hear me okay. I was having a bit of trouble hearing you there, Patrick, but I think I got the gist of most of what you were saying. Um, but yeah, so it's really nice to be here. Thanks very much for the invitation to give this presentation. I've been keeping an eye on the talks that you've been having recently, and yeah, lots of good speakers talking about lots of good things. So I hope I can give you something of interest today. It's going to be probably a little bit different from some of the other talks. I'll just share my screen actually, and we'll jump straight into it. Cool. Okay. So yeah, it's a bit of a sort of enigmatic title, I suppose, in a way. But the idea really is that I wanted to sort of get across kind of the range of scales that we quite often work in when thinking about Antarctica and climate. And that's scales in time and space. So, as Patrick said in that introduction there, I like thinking about things from the sort of century to sort of multi-million year timescale. In fact, I'd probably even refine that to say some of the work I'm going to show you is actually sort of sub-annual timescale, looking at sort of present day processes at fairly short timescales. Um, and of course, most of what I do is using numerical models. And so I started out my career as a field geologist and spent a lot of time in the field doing sort of mapping and sort of sedimentological work. So I'm very much a sort of observationalist by background, but I do find that models give us a unique insight into the way things work and allows us to sort of play with different possibilities and explore ideas. So for me, I guess I like bringing together that observational approach with the modeling and using each one to sort of help influence the other or inform the other. So we're going to have sort of three parts to the talk, really, and they're sort of they're sort of quite different, but they're sort of related. They're going to sort of scale up from the field scale, the observational scale, up to thinking about ice sheets at a more sort of generic sense, and behave over hundreds of thousands of years. And then towards the end, we're going to spiral towards chaos, hopefully not literally. But we're going to think about sort of Earth system responses at the very sort of largest scale. And what sort of goes with that sort of that change in scales is also the sort of degree of certainty, if you like. So as we sort of look at things in the short term, at the field scale, we have a greater degree of certainty on the things that we're observing. When we get to the very big picture, sort of Earth system type behavioral sort of insights, these are largely, unconstrained. We look at general patterns and behaviors, trying to learn something. But usually it's kind of, we're using sort of toy models to get conceptual understanding. And a lot of the time it's just about sort of playing with the idea of kind of what if. So sort of bear that in mind as we go through, that we're sort of dealing with a range of sort of uncertainties. Okie doke. So we'll jump straight into Antarctica. I didn't think that for this audience we needed to have the usual background of here's a map of Antarctica and these bits are melting because they're below sea level. I figured that you can know all that stuff already. So I just want to sort of situate a little bit with the kind of work that I've been doing over the last 10, 15 years. And typically we go down to the Ross Sea, like many of you working through the American program. And so we work along the transantarctic mountains or on the Ross Ice Shelf. And this is just an example of some of the stuff that, is looking a bit dated now. This is over 10 years old. But yeah, back in 2010, 11, we were down at the Beardmore Glacier and then up at the Skelton Glacier, two outlet glaciers of the East Antarctic Ice Sheet draining into the Ross Sea. And the reason I wanted to show this is because this is kind of, for me at least, the most direct way that we can use field data to constrain models. So what we were doing in these two locations, the top panel's showing the Ross Ice Shelf, sort of downstream of the Beardmore Glacier. The lower photo is on the Skelton Glacier, a little bit further north. But in both locations, we were doing geophysics. So on Beardmore, we were doing radar and GNSS surveys. So we were trying to figure out how thick the ice was across the grounding zone, and then figure out how fast it was flowing. And that gives us an indication of flux. On Skelton Glacier, we didn't have the radar that year, but we did install an array of GNSS receivers along the flow line of the glacier to try and get a sense of the sort of longitudinal flow rate, not just at the grounding line. And so on the left-hand side, what you'll see is a couple of sort of 3D maps there at the top with some little red dots. Those are showing the places where we had the GNSS receivers. And we've compiled that with ice velocity data from remote sensing from satellite imagery. And it's compiled with a bunch of other data sets that we managed to get hold of. There's some Croesus flight lines in there, a whole bunch of other things. So bit by bit, we've sort of pulled together as much sort of direct observational data as we can for these two glaciers, and then built these sort of flow line models to simulate their behavior. So the green dots, the green lines that go down the center line of those two glaciers reveals the path of the simulations that we ran. And on the sort of weird looking panels at the bottom there are showing the process of using those observational data to constrain them. So we start out with a flow line model. We can use a bulk parameter for a range of different things. And in this case, the blue dots are showing the sort of fit between our modeled and our observed velocities. If we just use a uniform deformation rate parameter, we assume there's no sliding and a single deformation rate for the whole glacier. And of course, that's completely unrealistic and it doesn't fit the observed data at all. So having the high resolution observational data allows us to go through this iteration process. So we can build a model, we can build a cost function into that model, which aims to minimize the misfit between those two things. And we iterate through that process until we get the brown dots there, which is obviously giving us a much better fit between the observed velocities and what we're simulating. So we can solve basically for those unknowns of the deformation rate and the sliding. So that's just my introduction in terms of sort of showing how we can use geophysical observations to constrain our models. And the purpose of doing that, obviously, is we want our models to be reliable. If we can reproduce the present day, then hopefully that means that they are at least capturing the right kind of behaviour, hopefully for the right reasons. Since then, we've shifted focus a little bit. We've moved up to the front of the Ross Ice Shelf, and the last few years, actually since 2019, we've had a small suite of GNSS receivers near the calving line of the Ross Ice Shelf, mainly around Ross Island, a little bit to the east of Ross Island, across the shear zone into some of the fast-flowing ice. And what we're looking at there is seasonal velocity change. Now, this is something that I became interested in back in about 2017 because people like Chad Green and various others had started publishing papers showing that there were velocity fluctuations on a number of embayed ice shelves around East Antarctica that were happening sort of on this subannual timescale for various reasons, and some of the examples that he was presenting, he sort of linked the velocity fluctuations to changes in the sea ice extent that was basically helping pin the ice shelf in some of those areas. So we asked the question, could that actually happen on a big embayment like the Ross, where things are wide open and sea ice can't really play such a big role? So we thought, well, let's go measure the signal, see if there's anything there. And hopefully what you can see in the sort of black graphs there, there is definitely a subannual velocity fluctuation. The magnitude is pretty small. We're talking about a few meters a year. In fact, in some cases, only a few tenths of a meter a year. But there is definitely a signal there. Something is happening on the ice shelf, causing it to oscillate at a seasonal timescale. We're yet to go back this season. Hopefully we'll get there and download the latest data sets and see what we can see. But in the meantime, what we've been trying to do is, again, use models to try and understand what's driving this. And we had a PhD student a few years ago, finally published the work last year, using ISSM to try and basically explore the possibilities, like, what do we have to do to the model to kind of reproduce this pattern of behavior? And we tried all sorts of different things, but it turned out that the most likely cause was basal melt. Buttressing from sea ice basically just doesn't do too much. Other groups have looked at this. Laurie Padman's group have looked at it, and they concluded that it was maybe a sea surface height influence related to sort of regional oceanographic change. And there's also possibly a sort of tidal forcing. But to me, it looks like it's probably a basal melt signature. And in fact, what we see is that in the areas where there's greatest basal melt, we see a stronger signal, which is a bit of a giveaway. And then kind of very recently, actually, this paper appeared, I think just a few months ago, which was super interesting for me because it gives, again, this mechanism. So this was a modeling-based paper, and they basically showed that there is this sort of subannual seasonal variation in the inflow of circumpolar deep water, which obviously drives up those melt rates. So it seems that mechanistically there's a sort of way to explain this, and hopefully as we go forward we'll learn a little bit more about this and figure out actually whether it's important or not. I mean, that's the bottom line. So that's the sort of fieldwork side of things. But of course, a lot of the observational data that we use to constrain models comes from remote sensing and indirect methods. So we're sort of scaling up a little bit here, and this is going back again a few years. But what we tried to do here was take simulations for the Greenland ice sheet and Antarctica and try and constrain those simulations with present-day observational data. So this was kind of an ambitious idea, really, trying to use a multi-parameter constraint to get the models right. But you can see there on the left-hand side, we've got a bunch of XY plots for net mass balance, surface mass balance, basal melt, and dynamic ice loss, so essentially calving. And what I was trying to do here was, through a sort of manual iteration process, get simulations for the two ice sheets under present-day conditions that fitted within the uncertainty of the present-day observations. And in those plots, the observational data are in the brown boxes. So my target was to get the blue lines to go through the brown boxes. Seems easy, but it took about 2 years because these simulations were pretty high resolution, at least for the kind of models that I run. And so they're pretty slow. But we got there, and we got simulations that at least agreed with the observations. So that gave us some confidence that they were at least capturing the mass balance and dynamic processes appropriately. And then, of course, we use that sort of that validated model to run forward in time. And that ultimately gives us what we think are fairly robust sea level projections, and you can see those in the bottom right-hand side. And in this the process of doing this work, we also explored the possibility of the ice-ocean feedback, which is something we'd looked at actually quite a few years before in a different context, but we realized here that basically that feedback mechanism can almost double the mass loss from Antarctica under certain conditions. So observationally constrained models are kind of my happy place, if you like. But one model is never really enough. It's no good trying to make predictions based on one model. So obviously a lot of what we do contributes to efforts like ISMIP, trying to do multi-model intercomparison. But this is an interesting area because this is where we get into model uncertainty, parameter uncertainty, and then forcing uncertainty. And everyone running models, we've got sort of 20 groups here, 12 models, everyone takes a different approach. So the question is, what's the right approach? Is there a right approach? So some figures here from the two papers on each of the ice sheets. They're different sizes, but I've tried to sort of scale them so that they're basically showing the same magnitudes. But what I really wanted to focus on is that sort of lozenge on the Antarctic box, showing that spread of model projections for 2100. You'll see that the Greenland projections are pretty well clustered. I mean, there's a spread in terms of the final sea level contribution, but they're all going in the same direction. The sign of change is the same. The trends are similar, but the magnitude is slightly different. Whereas for Antarctica, we've actually got a real spread, and the most concerning thing is that some of the spread straddles that zero line. We've got a change in sign, which is a bit of a worry. So when we delve into that, we can look at the different models and see what's happening. And what it turns out is that a lot of the models are basically capturing basal melt that's far too low. So when we look at modern melt, we think it's about 1,500 gigatons per year. You can see there that nearly all of those model members are below that line. And so that kind of reflects the different approaches. We take the approach of trying to tune to the observation. So our fit is the orange line, pretty close to that 1,500 gigatons, at least under present day conditions. But a lot of models start with a sort of data assimilation approach where they take surface velocities, invert for basal traction, and then run forward in time. Unfortunately, unless you're getting the mass balance components right, then you can end up with very different outcomes. So there's there's a sort of lesson here, at least in terms of how we think about models. We focus a lot on improving sort of model physics and model numerics, and that's great. Um, it's an important part of the process. But unless we're actually using field data, observational data, to make sure the models are doing the right thing, then we can't just use them out of the box and hope that they're going to do a good job. And this is important, right? We've got to get the projections right. This is stuff that's getting used by IPCC and hopefully informing policy, right? So it's got to be right. Sort of extending from that, we can look at not just taking that sort of spread of models, but then trying to emulate that model spread and trying to fill in the gaps of a whole bunch of unmodeled parameter combinations. So this is work that Tamsin Edwards and other people have worked on, building, in this case, a Gaussian process emulator to try and understand what the uncertainty is on some of these projections. And the thing that's kind of interesting in terms of the sort of two ice sheets, you can see there on the bottom left, the Greenland emulated projections give very clear scenario dependence. When you go up to the warmer scenarios, the higher emission scenarios, you get a much bigger sort of separation between the simulations, and the sea level contribution goes up. The same is not true for Antarctica on the bottom two panels, East and West Antarctica. There's very little scenario dependence there, which is kind of intriguing, and it makes you wonder what's going on. And the bottom line is that the scenario dependence for Antarctica doesn't actually emerge by 2100. So when we're thinking about sort of policy guidance, running the sort of ISMIP type simulations to 2100, it doesn't actually capture that long response time of the Antarctic ice sheet. And to really capture that, we've got to run to 2200, 2300, something like that, which again becomes a challenge for some of the models that are participating. I'm not showing it here, but we do obviously have the ISMIP 2300 simulations, which have tried to address this. So there's a lot of kind of interesting insights coming out from that as well. We're now sort of extending this sort of process within our group. As I say, the previous sort of approaches, both the Tamsin Edwards Nature paper from 2021 and also the work I just showed that we did for Antarctica, they were both using Gaussian processes to emulate the ice sheet response. We recently started some work trying to do the same thing for Greenland. We have a new postdoc with us, Peter Sue. Some of you may know him. He was Lamont Doherty until quite recently. He joined us last year. But he came in and he sort of picked up the Gaussian process emulator and tried it out and said, nah, we can do better than that. So he very quickly built an artificial neural network to do the same job, but in a much more efficient way. So what we're doing now is we're running a sort of Latin hypercube sort of approach, running a whole bunch of PISM simulations using the ice sheet model to explore a whole bunch of parameters, a whole bunch of different forcings, and then use that to train the emulator. And what Peter's able to do with that is to build the neural network in a way that allows us to not just explore lots of different parameters to sort of capture the variations that come from both ice flow and mass balance parameters, but also to explore different emission scenarios. So it's looking pretty good. This is work that's still underway. We're still sort of working on this. But the really nice thing about this is that you can train the model, train the emulator, and then explore a whole range of scenarios that you didn't run the ice sheet model for. And you can run thousands, tens of thousands. And this is what Peter's been doing over the last few months. Very quick to run, of course, makes it very cheap to do these experiments. And it allows us then to basically do the history matching, which is the key thing. Again, it comes back to sort of matching to those historical constraints, the observational constraints. We can run tens of thousands of emulated scenarios and then select the ones that fit the observations. And so we can see here a spread of results from different GCM forcings. And we can do all sorts of things to them. But you can see there in the top right-hand side, Just one example, if we take the original spread of simulations, the original sort of parameter set, we can look at the fractional uncertainty that comes from different sources. And the green basically, I think, is showing you the ice flow uncertainty. I think it's ice model uncertainty. The orange is what's coming from the emissions scenario, and then the blue is the GCM uncertainty. Now, we can do that for the unconstrained parameter set, but then doing the history matching, we then modify that. So we can then take the ones that just fit the observations, and we can see that actually the pattern, that fractional uncertainty distribution looks quite different. And it makes it pretty clear that actually the biggest uncertainty in terms of future projections, once you get past the end of this century, is all down to emissions. So it really hammers home this idea that the emission scenario is everything, pretty much, once you get beyond this century. So that's the sort of first part of the talk, probably the longest part of the talk, thinking about how we use observations to constrain models to do future projections to hopefully inform policy. Now, the next bit is not really about policy. It's about something a little bit more generic. It's about sort of fundamental questions. And this is kind of relevant, right? Because all the stuff we've done previously, all the stuff we've been looking at, is all based on this understanding that, we know how the system works. And we often use paleoclimate proxies to inform our projections. In fact, if you read any kind of paleo paper, it usually starts with some sort of sentence or paragraph that says something along the lines of understanding the past is essential to better constrain future projections, right? So it's that's the justification for a lot of the geological work that's done. And yet we find ourselves sort of taking on board a whole load of sort of assumptions, and we never really test those assumptions. And one of the big assumptions is that, when it gets warmer, the ice sheets get smaller, and sea level goes up. And that seems fairly intuitive. But we do have to ask the question, is it right? Is it right under all conditions, under all climate states? Are the responses of an ice sheet uniform through space and time? So the next few slides are sort of exploring that idea. And as I mentioned at the beginning, we're going to get sort of progressively more sort of conceptual as we go through. But what I'm showing here, that funny blob thing, is my simplified ice geometry. It's an ice dome, a radially symmetric ice dome that is about 3,000 kilometers across, or at least, sorry, the domain is about 3,000 kilometers across. It has a fringing ice shelf. And the way that this model is set up is intended to be sort of representative of East Antarctica. So it's not realistic, but it is representative. So the climate state and the sort of bed elevation and so on. And we've simplified the geometry and we've simplified the forcings in order to be able to run very long simulations. So we're talking about, in fact, the suite that I'm going to show you examples from adds up to about 100 million years of simulation. So there's a huge amount of computation involved. So it's got to be a simplified ice sheet, or at least a simplified ice sheet geometry. But the key thing here is that we're applying the sort of full physics. And I say full physics there in inverted commas because this isn't a full Stokes simulation. This is a hybrid stress balance model with shallow ice approximation, shallow shelf approximation. So it's simplified in that sense. But what I mean by full physics is that this is using the same physical schemes as I would use for those much more realistic high-resolution simulations of the ice sheets for projection work. So we're not simplifying any of that. So the one thing that comes out of this is just two examples here to kind of give you an indication. If we simulate or drive this ice sheet with what I'm calling a warm atmosphere and a weak ocean, you can see that under the interglacial warm conditions, the ice sheet actually gets bigger, and in the glacial, it gets smaller. which is a little bit counter to that sort of that key assumption that I mentioned before. Panel C is much more kind of what we would expect, that when you get the glacial cold peak, the ice sheet advances, we see the ice shelf extending, depression of the crust, and then as the warmer atmosphere of the interglacial kicks in, then the thing retreats. So those are just kind of two end member scenarios. We see completely opposite phasing. Now, those are just two examples from a whole suite. This is just showing part of the ensemble. So what I've been doing is running, as you can see, 6 different atmospheric forcings going from sort of left to right against 5 different ocean forcings going top to bottom. And we run that for sinusoidal climate forcings. So the ocean and atmosphere are oscillating in magnitude with a sinusoidal forcing that varies in wavelength. So the periodicity in this example is 100,000 years and running for 500,000 years in each case. Also ran the same for 41,000, so yeah, 41 and 23,000. So you can imagine that this ensemble of 30 simulations is duplicated for each of those. So we end up with a sort of 90 simulations. What we're showing is the ice volume in the blue line, and then area and brown, carving in green. That's all too much to look at, so we'll just take a few examples here. Now, when things are simple, looking at panel A, if we have an atmosphere that's relatively cool, so the grey line in panel A at the top, and an ocean forcing that's relatively weak, that's the black line. If they're constant, i.e. there's no sinusoidal variation, then funnily enough, the changes in ice volume are very, very small, and area and carving fluxes are, there's some oscillation there, but there's nothing periodic. It's just sort of white noise. Basically, they're constant. That's exactly what you would expect. If we jump to panel B, what we're doing here is we're driving it with this is the warm atmosphere scenario. You can see the grey line is quite high on the graph, so it's a warm atmosphere, a weak but constant ocean forcing. And in that case, we see an ice sheet that's oscillating. The blue line there, the volume, is oscillating in phase with the forcing. So as it gets warmer, the ice sheet gets bigger. And that's because the air temperature is tied to precipitation. So the accumulation basically goes up as it gets warmer. And the other parameters, area and carving, follow that. Let's look at panel C. We've got a very different scenario here. We've got a very strong ocean forcing now, and a cold but constant atmosphere forcing. And we see kind of the exact opposite, right? Now we're seeing an ice sheet that is getting smaller during the interglacials and larger during the glacials, which is kind of what we'd expect. Now, the interesting things start to happen when you have both the atmosphere and ocean oscillating in phase. So we jump to the bottom row there. We've got the ocean atmosphere oscillating in phase, but in the first example, we've got a warm atmosphere and a relatively weak ocean. So that in-phase response is still dominating. The ice volume, the ice area are still oscillating in phase with the climate forcing. If we make the atmosphere a bit colder and the ocean forcing just a bit stronger, something kind of strange happens. Now, all of a sudden, the ice sheet is trying to advance both during the interglacial and during the glacial. Okay, so now the two things are competing against each other, and we end up with this sort of half period resonance, essentially. So we're putting in 100,000-year forcings, but we're getting out a 50,000-year resonant. So when we're thinking about interpreting paleoclimate proxies, if we're seeing a cyclicity of 50,000 years, it may not be that there's a 50,000-year driver. It might just be this resonant pattern that's arising from the interplay between the ocean and the atmosphere forcing. And of course, you can apply that thinking to any other sort of Milankovitch frequency or anything else. Now, of course, you go to the far end member there. We've got a very strong ocean forcing now and a much colder but still oscillating climate atmosphere. And you see something quite interesting now. We've got the antiphase forcing, sorry, the antiphase response in the ice sheet volume, but we're seeing a sawtooth pattern. So we're seeing asymmetric ice volume changes now, which is kind of interesting. And this arises from bed, the isostatic effect. So the bed is being depressed, and it's delaying the regrowth of the ice sheet. But it's kind of interesting that we can get a fairly complex ice volume signature from just putting in two very simple sinusoidal forcings. So there's something kind of interesting just in terms of that sort of forcing signal. And what I've tried to explore through this ensemble is just that sort of phasing relationship. And so taking each of those frequencies and plotting each of those climate forcing combinations, you can see these sort of matrices. The red numbers basically tell you the correlation coefficient, and the colors of the heat map reflect that as well. So we can see that there's this diagonal across each matrix that you go from a sort of strongly anti-phase response to a strongly in-phase response, and somewhere along that diagonal is where you get that sort of that resonant frequency where the ice sheet is kind of not quite sure what to do. So there's different sort of regimes, if you like, of behavior. And this is kind of where we then take it. Let's think about regimes in terms of not just the sort of phasing, but in terms of what's actually happening behaviorally within the ice sheet. What I'm plotting here in the top panel on the left-hand side is the mass balance components. In fact, what we're focusing on is just mass loss components. We're looking at calving in grey, subshelf melt in light blue, and surface melt in dark blue. And these are transient simulations now, so we're taking the same basic setup as we had before, but instead of just running kind of a constant in time but sinusoidally varying forcing, we're now applying a linear ramp to that sinusoid, as you can see there. And so we plot the magnitude of the mass loss from each of those components, and you can see that there's some variability, and lo and behold, at the colder end of the spectrum, at the beginning of the run, you can see that the mass loss is peaking. The subshelf melt is peaking during the cold periods because the ice shelves are much bigger, and towards the end, the sort of phasing is actually in phase rather than anti-phase. And what's actually really interesting to me is that when you normalize those components and basically look at them as a sort of fractional contribution instead of in terms of their absolute magnitudes, something really interesting pops out. If you look at the sort of left-hand side of panel B, the light blue there, it doesn't vary at all. So basically this is telling us that the fractional sort of makeup of the mass loss signature doesn't seem to change a whole lot, regardless of whether you're in an interglacial or a glacial state. When you're under a very cold state, basically the magnitudes change, but the fractional component stays the same. And one way to sort of understand that sort of within ice sheet variability in the sort of multi-parameter sense is to look at the entropy signal, the Shannon entropy signal. So that's basically telling us something about the variance within those different parameters, the predictability. And you can see it's very low at the left-hand side. And as we get into the more variable signal, the entropy signal, entropy value gets much higher. It's a much less predictable signal. And the bar chart on the right-hand side, panel C, shows you that there's a sort of bimodal distribution there. So we've got one state where there's low entropy, one state where there's higher entropy. On the bottom, we're showing the exact same data, but now I've just shuffled those data. So instead of being in the time domain, we're now putting them in temperature space. So now we're looking at what's happening as a function of temperature. So it's a state space projection rather than time domain. But you can see that this regime shift basically pops out really nicely. Now we see that under the colder situations, it's a much more predictable low entropy state. Under the warmer sort of intermediate conditions, it's a much higher, much less predictable state. And then you drop down to a low entropy situation towards the end where the mass balance pattern changes again. Now, that's all well and good, but that's a very smooth, what I've done there with the entropy signal is I've smoothed it 100,000 years to try and get rid of any glacial interglacial variability. If you look at the 100-year smoothing, the pattern's quite different, but it's kind of interesting. So it's the same data, but we're just applying less smoothing. Now, what's interesting is that it's a much more variable signal. That pops out straight away. We don't see as much evidence of that sort of bimodality there, at least in the bar charts. But if we jump to panel D, I think the same signature is still there, right? So we just go back to the last one, we see this sort of low entropy, looking at panel D, low entropy, high entropy in the middle, and then low again. And we see the same thing in panel D here. But what's interesting is that intermediate state is much more highly variable. We start seeing this sort of flickering associated with the sort of mass balance signal. Now, if we look at the exact same forcing, but with an increasing basal melt, we see more or less the same sort of pattern. So there's something kind of interesting happening there, that it's not just the magnitude of the entropy signal that's changing, but it's also the variance that's changing. And we can summarize all that in this one panel. So when we were looking at the phasing signal at the beginning, we were seeing that sort of period doubling, that resonant frequency, and that pops out kind of nicely in these transient runs in that top panel. The entropy magnitude is shown in the middle panel, and the variance of the entropy is shown in the bottom panel. And I think there's some pretty clear evidence there that the ice sheet is basically going through these different regimes. And the question becomes, why? Why is it doing that? And I'm still working on that. That's why it says to do. It's not that I didn't finish the slide, it's I haven't finished the work. I'm trying to understand the mechanics of this. I think there's something to do with an ice softening signal. So if we look at the bottom panels there, something's happening in the ice softening. So the left-hand column is showing you what's happening in the ice shelf cells, the floating cells, and the right-hand side is telling you about the grounded ice. So clearly something's happening to the ice softness in the ice shelf. But the other thing that I think is kind of interesting is if we look at the second panel down on the right-hand side, this is the basal sliding of the grounded ice. And you can see that around 4 degrees above present, we start seeing an uptick in that basal sliding, as if there's a new regime, a new dynamic regime switches on at that state. And all of a sudden, more of the ice sheet starts to slide at its bed. So there's still some work to do there. And it's, it's something that hopefully we'll get to the bottom of. Okay, so I've got hopefully just a few minutes to spin things out to the much more conceptual big picture stuff. We looked at sort of ice sheet responses at the subannual timescale. We've looked at them over the 100,000 years timescale. But what about climate over millions of years? You know, how do we understand climate over very long time periods? And this is kind of relevant again to how we use proxies to make inferences about ice sheets, because there are key periods of the past, periods like middle Pleistocene transition, where something happened, not in the climate forcing, but in the Earth system response. We saw a big change from, or a gradual transition, basically, from a 41,000 year dominated world to a 100,000 year world without any apparent change in the forcing. And the forcing there, Milankovitch forcing shown in the top panel on the left there. So the question is why? And it seems that one of the big possibilities is that it's to do with gradual cooling and a change in the extent of marine-based ice, particularly in Antarctica. But the trouble is, whenever we've run deterministic models, lots of Earth system models, coupled GCM, ice sheet type simulations, they've all come up with slightly different interpretations. They've all come up with different sort of mechanistic understandings. So that's often because we can't include everything in these models. So what we tend to do is we tend to sort of put in a new process and look at what happens, and we fiddle with the parameters and we say, oh yeah, actually by including this process, we can now simulate this transition. And that's great, but when lots of different groups do it and they all come up with a different answer, we sort of start wondering, well, what is it? Is this a model-dependent answer, or actually are they all right, but for a slightly different reason? So I've been sort of trying to get my head around this. And I think there's something interesting to just understand from the panel on the right-hand side. What we're doing here is just looking at the sort of last 800,000 years, looking at the Epicodome C record in the blue line, and the insulation forcing in orange. Now, if you normalize those two things, basically so that they're on a similar scale, 0 to 1, or sorry, -1 to +1, and then difference the two, you get a sense of the sort of mismatch between the incoming forcing and the sort of global Earth system response. And so that's what's in the gray shading. That's what I'm calling the disequilibrium, if you like, of the climate system. And you can see some interesting things here. So just after stage 51, for example, insolation was very high. Temperatures were actually pretty low. Stage 11, the insolation was actually pretty low, but the temperatures were very high. So kind of different responses. Now, the fact that you can get such different sign of disequilibrium through time suggests that there's something obviously in addition to that insulation, and that of course has to be Earth system feedbacks, carbon cycle, and so on. So by taking this very simple approach, you can start saying something about the varying strength of different feedbacks through time, which comes back to this question of how we address the MPT. It's all about the feedbacks. Which feedback do you employ? Now, if you look at one particular period, you might find that carbon cycle is the best explanation for what you're looking at. If you look at another time period, it could be something else. It could be regolith, could be isostatic depression, could be sea ice switch, all these different things. So we need to understand feedbacks a little bit better, I guess, is my sort of perspective there. Now, one of the things I've been playing with for a little while is just sort of using very conceptual dynamical systems approaches to try and understand feedbacks. And this is a very well-known example. This is something known as a logistic map. It's a simple equation that basically iterates through time. And you can see there in the top left that if you take different values of lambda, so basically just a coefficient within that equation, and run the exact same calculation, you end up with a scenario where the system evolves as you go up through those panels, different magnitudes of sort of stable behavior. Then you get into oscillatory behavior, and the gray lines are all oscillating sort of system states. Then you get into the blue panels there where you're getting period doubling. So this harks back to what we saw in the previous section. You start seeing the system behaving in a way where the period of its oscillations starts changing. And then as you get into those red scenarios, you get more towards the chaotic end of the system, and eventually the whole thing blows up and you end up in a chaotic regime. Now, that animation hopefully sort of illustrates that point that if you take a linear forcing and run through that lambda, if you increase lambda linearly, you step through each of those states, but you end up with something that evolves in a way that is highly non-linear. So the response goes through a sort of step change and then a slow increase, and then it breaks down into chaos. Now, it turns out that you can use that approach and turn it into a glacial cycle. So on the bottom panel there, is that logistic map, forced now with a little bit of white noise to add some sort of random variability. And we've imposed some conditions. So basically, if it gets to a chaotic state, we allow the system to collapse and then recover rather than just blow up the model. And what we can see, hopefully, in that is that we can mimic what we see in the ice core record. So this is EDC for the last 400,000 years. Now, the idea isn't to reproduce the ice core, but it's just trying to understand that we have similar kinds of states. So we see this sort of peak interglacial that's short-lived. And then we have this sort of cooling phase, sort of rapid cooling phase in the blue. And then a sort of much slower approach to the glacial maximum in the yellow, and then the abrupt warming in green. And you can see I've just highlighted with the circles the sort of glacial maximum and the interglacial maximum states. And we see the similar sort of behavior reproduced with that logistic model. So these sort of approaches are very conceptual, they're very sort of poorly constrained, but the point is we can learn something about the system by taking this approach. And it tells us that if we have a chaotic system forced in a linear way, for example, just by changing albedo, we can reproduce much of what we see in the Earth system response. So that's kind of cool, but that only explains one part of the problem. If we're trying to understand, something like the MPT, we're simulating those asymmetric cycles quite nicely. But why did they become asymmetric in the first place when we had nicely sort of sinusoidal oscillations beforehand? Now, the thing that's sort of evolving on the left-hand side here is a sand pile model. This is another very simple conceptual model that people use in dynamical systems work. All we're doing here is we're taking a square domain where basically, if you imagine sand flowing through an hourglass and falling in the middle as that pile builds up and then collapses outward, it then sort of builds up again and collapses outward and carries on. That's basically what we're doing here. We're allowing the central cell in this domain to build up by a value of 1 every time step. We're not adding any mass to the rest of the domain, but what we are doing is we're allowing that central cell to collapse when it reaches a critical level. And then, of course, the neighboring cells start to build up and they collapse when they reach a critical level. And you can see increasing complexity. And what you're hopefully beginning to see now is that there are sort of ripples. That was quite a good one. There's these sort of waves of reorganization that sweep through the system. And this is basically telling you that there are collapse events that are taking place across the whole domain in a sort of fairly synchronized way. Now, if we distill that into a time series, you get these patterns here. The top panel shows you the evolution of that, the sort of average pile height, as I'm calling it, in the blue line. And the grey bars show you the number of collapse events that are taking place. And you can see that the number of collapse events increases through time. But what I really wanted to focus on is those middle 3 panels. What you see at the beginning, when the system is small and relatively simple, you're seeing kind of near symmetric oscillations. So the system builds up, it collapses. It's pretty intuitive. But as the system complexity increases, you've got more coupled components interacting with each other, it becomes increasingly asymmetric. And we see that as we get to sort of panel D there, you can see this highly asymmetric oscillation by the end of the simulation. The bottom panel is just a wavelength analysis of the collapse events, and it's basically showing you that the collapse events, even though they're becoming more numerous, they're becoming more spread out. So the frequency is going to sort of longer periods. Okay, so becoming basically there's more collapse, but it's happening less frequently. Now, my interpretation of that is it reflects increasing synchronization. And that's what this inset shows. This is the proportion of the active domain that is synchronized. So there's something we can learn here about the Earth system in terms of system complexity. As we build the complexity of the system, we bring more components into play, then there is a greater potential for them to synchronize with each other. And that can lead to some interesting emergent behaviors. So if we try and sort of wrap all that up, we've looked at things in the dynamical system sense. We can understand the climate oscillating between sort of what I've called quasi-stable limits. The take home really, I suppose, is that when things they build up towards a glacial maximum state, that's probably a state that's quite unstable, which is sort of counter to what we might think. We might think when things are sort of cold and dry, it's about as stable as it can be. But actually, I think the glacial maxima are times when the Earth system is at its most connected. We've got the most extensive marine-based ice, we've got sea ice, we've got a lot of Earth system components, which are all kind of interacting with each other. And it means that a perturbation to any one of those can then ripple through the whole Earth system. And that's why you get these rapid collapse events. And that's why I think when it comes back to sort of theories about the MPT, I think they could all be right. And that in a way, it doesn't matter what the trigger is to trigger these sort of rapid transitions. The glacial terminations. It could be any one of them because each component is sort of poised at that critical state, ready to collapse. And when it does collapse, it cascades through the entire Earth system. So as I say, very unconstrained, very conceptual, interesting food for thought. No doubt probably upsets a lot of people, but I find it interesting. These are my sort of take-home messages. I want to take you right back to the beginning. Observations are essential primary data. I think anything we do with models has to be based on models that are constrained by the observational data. It's only by doing that that we can make robust projections. But the advantage of using models is that they allow us to explore things we haven't yet experienced. So that's the value. We can observe things, we can use the observations to constrain the models tell us about things that may happen in the future that we haven't yet experienced. And the take home from the more conceptual things, hopefully, is that we have to be prepared for chaotic changes, abrupt changes, cascading changes that can affect the whole system. Thank you very much again for inviting me to give this talk. I hope there's been something of interest there, regardless of your background. Happy to take questions, and yeah, thanks again.
Thanks very much, Nick. Do we have, yes, Gavin has a question.
Hi, Nick. Thank you very much. Nice work. A few questions though, right? That you kind of touched on, and I'd like to hear you kind of dive a little bit more deeply into that. I mean, we have had you say, well, we have to base everything, constrain everything by observations as best you can. But as you point out, in an observation limited world with a lot of variables and potential choices within the modeling system, one can overfit a model to a subset of the data and then make predictions which are totally wrong. And you can get, as you mentioned, multiple groups fitting the same data using different processes and all providing different predictions. And so you might say, okay, well, we just need more data and more data and more data, and we'll winnow it down. But the amount of absolutely new data that we're going to get is pretty small, right? You know, so it seems to me that we're not going to get new data fast enough, and certainly not faster than we can think of new processes. And so where do we end up? Do we end up with a situation where ice sheet models are just going to ever increase in uncertainty as the number of potential pathways for change increases, as the complexity increases, and the number of data points which we have to constrain that is not going to be enough to be able to say?
Yeah, I'm totally on board with this. This is something that I've talked a lot about actually at different sort of times in the past, but this idea that we're sort of obsessed with making our models more and more complicated in order to take into account more physical systems that we've just discovered might be important, and so on. We're always adding more physics in the hope that we can make more robust models to make more robust projections. But actually, what's happening is that we end up with more and more models that become harder and harder to constrain. You're absolutely right, and it's not just about sort of having the observations to constrain them. It's about the fact that we have emergent behavior, right? And this is something that that last part of that talk really sort of gets at. As soon as we start coupling models, it doesn't necessarily mean we have a better representation of the Earth system. It means we have a much harder to constrain representation. We have a model that actually behaves kind of a lot more unpredictably. It becomes a lot harder to get the model to stay stable. We have all sorts of feedbacks, which might be amplifying feedbacks, which mean that the whole system blows up. It becomes very, very hard. And then you're sort of in this sort of exponentially increasing world of constraint possibility. Like you've got so many components of the model, then what can you possibly constrain? So you end up having to simplify it. You end up having to sort of smooth things, or you do the ensemble approach and say, well, let's just take 100 or 1,000 different ensemble members that explore this parameter space and look at the mean. I don't think there's a single answer. I think we kind of have to do these things because that's the nature of scientific exploration. But I guess the key thing is the more we explore, the more the uncertainty is going to increase. The tricky thing is sort of explaining that to our end users and stakeholders. There's a nice graphic that was on the social media a while ago, which basically sort of showed a cube of like the difference between what a modeler does versus what a politician wants. And it's kind of like, the modeler wants sort of to explore as much parameter space as possible, to explore as much uncertainty as possible. Whereas the politician just wants one answer. They want to know, like, what is going to happen over this time period and tell me with certainty. I don't think we will ever get to that state. So our job, I suppose, is convincing those end users that they need to be able to live with uncertainty and that there's value in that uncertainty.
I mean, that's a bit of a bit of a stereotype. I mean, I think politicians that I've talked to and decision makers are actually quite okay with uncertainty. They make decisions under uncertainty all the time. Our conceit is that physics is more reliable than economics, which I think is valuable. But they make economic decisions where they have even less insight into what's going to happen. I mean, witness what's been happening the last 3 weeks. Much of that was in fact predictable, but people make bad decisions anyway. I wanted to throw something else out there. I mean, a lot of the dramatic shifts that you're seeing there, those are on pretty long timescales, and I'm not saying that those are not interesting questions. Of course they are. But on the more salient timescales, the years, decades, we have some hope of being able to do better in terms of processes because we have satellite data, we have in situ data, and we'll have more of that as time goes on. One of the things that's been happening kind of interestingly around Antarctica is that there does seem to be an interesting play between sea ice, meltwater, and accumulation on the ice shelves that seems to be a kind of complex thing, and we've not been able to explore that because we don't yet have models that have the ocean and the ice shelf cavities and the sea ice and the interactive ice streams and ice shelves. So we haven't been able to really dig into that. But I'd be interested to know whether those kind of short timescales and the possibility of complex interactions between all of the different ocean sea ice, ice shelf, ice sheet interactions is something that you guys are exploring, or because there's complexity and perhaps chaotic behavior there too.
Yeah, right. So I guess the more components, as you say, that we bring together, the more we're going to see those sort of emergent responses. The problem is always going to be if we have observational data, how do we disentangle the drivers? So we can say, yeah, we're simulating an increasingly complicated, maybe even a complex system, but trying to do the attribution, I don't know, that's something that you're very familiar with, is is really, really hard. So yes, we can look at what's happening now over short time scales and try and make some inferences as to the sort of feedbacks within the system that are leading to a particular signal that we're seeing. But ultimately, I think we're probably still a way away from predicting with certainty any given event, right? I think it comes back to the understanding of the signal and the sort of variability in the signal. And this sort of also comes back to what we were just saying about politicians. I appreciate your point about them making decisions under uncertainty all the time. But I guess the key thing is that we can have simulations that predict the likely behavior of a system with quite good accuracy, right? We can predict the stochastic sort of regime, but we can't say with precision, next year will be like this, the year after will be like that. We're not yet at the sort of weather forecasting stage with ice sheet behavior. And yet that is kind of almost what planners want, right? It might not be what politicians want, but when we talk to planners in the sort of local government level who are actually sort of investing money in seawalls, road infrastructure, a planned managed retreat type work, they want to know, like, when is it going to be that sea level will be at 0.5 meter above present or 1 meter? We need to know, like, within a few years. They need something quite specific. So being able to predict a system behavior is one thing, but being able to predict it with absolute precision is, unlikely.
Well, I mean, in weather, we've got used to, and I think end users have got used to the idea that you don't have a 60-day weather forecast, right? And that it's not a question of us not being clever enough; it's just not possible. But it is also something that we can say about the statistics of intense rainfall, that those are increasing, and that we have a longer term predictability of that than we have of weather forecasts themselves. And so, depending on where your predictability is coming from, you can say, things that are still useful to different folks. But let me let other people speak. But I don't want to despair.
Oh no, definitely not. I don't think we need to despair.
Anyway, thank
It's
you
all
so
about
much.
Lynn.
Hi, yeah, thanks for a great talk. Yeah, I was really interested in like the Pleistocene part of your work, and I was just wondering, one of your conclusions was about like the increasing efficiency of the system through the Pleistocene, and I don't think I quite understood that part of it. I guess it was, yeah, just was hoping if you would elaborate a little bit on that part of your work.
Yeah, I didn't really say anything about it, efficiency. I put it on that slide, but it's interesting that you picked that up. The way I'm thinking about it is that systems tend to have a way of evolving towards greater efficiency, right? But they're always competing against other feedbacks. You could think of sort of classic sort of three-body problem, right? We've got sort of gravitation as this sort of concept of a body falling towards another, but it's the body's in motion, so we end up with sort of rotating around each other. So the system's trying to evolve to a state of essentially lower entropy, right? More efficient. These two things want to be together, but one of them's moving, so that means the other one has to keep moving, and they rotate around each other. So I kind of like to think that the climate system is doing something similar, that it's trying to basically find some comfortable state to be in. But unfortunately, that comfortable state keeps changing. Now, if we try and sort of really blow things out and look at everything from like the climate of the Archean back, back 4 billion years ago and bring it forward through time, you can say, well, the climate has become a lot more predictable through time. We don't have magma oceans anymore. We don't have massively elevated CO2. We actually have oxygen in the atmosphere. There are these sort of nice things that have evolved through time. So you could say that there's some sort of Gaia type process going on where there's these sort of interactions that have enabled the Earth system to sort of settle down to something sort of predictable. In terms of the Pleistocene, it's an interesting thing. We think we know kind of how the system has behaved over the last 5 million years, but we still don't have great resolution on a lot of the records except for sort of snapshots. So we don't really know kind of how the system was behaving as a whole. Yeah, it's something that I'm still kind of exploring. I like the idea that essentially the growth of asymmetry in the climate system was something that allowed for abrupt reorganization, right? So it's sort of a slow growth towards a state which allows for collapse, that allows for reorganization. I think no matter what Earth system or natural system we look at, that seems to be kind of a repeated sort of pattern of behavior. We didn't necessarily see that in the Pliocene. We tended to see much more sort of linear response to forcing, sinusoidal response. But we can see asymmetry in the Miocene. So there were periods when things were oscillating there. So yeah, I'm happy to hear your insights on what you think as well.
Yeah, I wasn't sure if you just meant that it was like kind of the efficiency on it, like becomes more efficient to collapse an ice sheet through the Pleistocene, which I think is an interesting way to frame it as well. Or more rapid retreat and perhaps to a full collapse of an ice sheet. Whereas perhaps we didn't have that in the early Pleistocene and in the Pliocene.
Yeah, no, you could look at it like that. I mean, once we get a marine-based ice sheet in Antarctica, then it becomes a lot easier to drive rapid retreat. When the thing's just terrestrial, then it's very hard to retreat a terrestrial ice sheet. You can't do it very quickly. So that expansion of marine-based ice gives you that vulnerability, partly because of the low profile, but partly because it gives you a much stronger connection to an additional Earth system component, i.e. the ocean. So there's a change in complexity there of the system because you've got a change in connectivity. So yeah, I would guess any time when you see those connections being established, it gives you the potential for much more rapid change.
Yeah.
And cascading changes.
Yeah.
Cool.
Thank you.
Thanks.
I don't know that connectivity per se must be destabilizing, right? The whole system is obviously as connected as it is, and in fact has been extremely stable if you think of it on a 4 billion year timescale, right? So is there not also an argument that greater connectivity allows for more negative feedbacks to actually kind of apply that actually stabilizes the system?
It's possible, but I don't think it's as simple as that, and I don't think it's a binary
I didn't say
state
it was simple.
if you imagine a system composed of half a dozen components that are all completely isolated, it's going to be very stable, right? Because they're not interacting with each other. So one of them can fall over, but it doesn't affect the others. Once you have a system composed of connected components, it can be stable, right? I'm not saying it's not stable. What I'm saying is that if they're all connected, collapse in one has the potential to trigger collapse in another, right? And we know this from graph theory. You've just got to go to graph theory and look at some of the papers on how a collapse cascades through networks. We see this in the financial system. We see it in social networks. Network models show this kind of behavior very, very clearly. Connectivity is everything in terms of enabling collapse. It doesn't necessarily predicate that it will be an unstable system, but it enables instability to propagate.
Yeah, but well, yes and no. I mean, so we've had like 5 mass extinctions, right? I mean, no, we're talking right where the system did totally collapse, right? Massive changes in the oceans, anoxia, eunixia, everything dies, and then it has to start again. But for most of the rest of the time, things didn't change that dramatically, right? Water, like liquid water, has stayed on the surface of the ocean, on the surface of the planet for 3.5 billion years, right? And you think about planets such as Venus, Mars, things collapsed much faster for various reasons, and yet the Earth is relatively stable compared to those, right? And maybe that's because there were more elements, that the oceans were bigger, that we had the potential for ice sheets. I mean, we had plate tectonics. It's very hard to it's very hard to claim that the complexity in and of itself is destabilizing. I think the more unstable planets are the ones that were simpler.
Yeah, I don't know anything about other planets, to be honest. Actually,
That's okay. That's okay. I'm taking things way beyond. Way beyond. See, but this is the fun thing that you work for NASA, and then suddenly there's a whole bunch of astrobiologists that pop in, and suddenly you have to think about things on a much bigger scale than exactly just what is going on in the Amundsen Sea right now. So, anyway, sorry. Thank you.
Okay. Any other questions? I guess we can stop there. So thanks again, Nick. And
thank you very much. It's good to be here. Thanks for all the